Hey, hi, everybody. I assume that you can hear me. We're going to wait a couple of minutes. We have 20 people here so far, which is a good size audience for this talk. Just a few ground rules. When you come in, please put your video off and mute yourself. We're going to use the chat facility in order to ask questions during the talk. If something comes up that you'd like to hear more about or that prompts a question, just use the chat facility and type something in. At the end of the talk, time permitting, we'll go through at least some of the questions. If you have to leave the talk early, or if there are friends of yours who were not able to come today, we know the URTEC convention is running, for example. This talk will be recorded, and this and the other 26 talks, the full recordings of them are on our website, www.petrolern.com. So at your convenience, you can come back and replay those, which is a good thing. Our next talk is on July 24th. Dr. Femke Voskuil from the Netherlands will be speaking, and it's a real interesting talk, as is the one today, but this one is a little out there because she has been using geoscience data methods in order to track and try to have an positive impact on the COVID-19 virus. So I got intrigued with that. I contacted her and got her on that. Okay, so our talk today is by Dr. Angela Goodman, who's a research chemist at the National Energy Technology Laboratory. And Angela will show you a map of where NETL is and where the other national labs happen to be. And this talk is on estimating prospective CO2 storage using a tool called CO2 Screen, which she may even have time to demo towards the end. And this is an open source tool, and it will be freely available, or is freely available to the public. I've known Angela for a few years when I was working at the Department of Energy. And so she's been working on coal and carbon storage, and then there are others who've been working more on oil and gas. And they all got together and put something together for me that I was able to use in a talk on technology integration, but it looks at the synergies and overlaps between, for example, CO2 storage and reservoir engineering or reservoir monitoring. And there's a lot of overlap, and that's probably why a lot of people who are in oil and gas these days, and for very good reasons, are starting to look at how they can have an impact on carbon storage, carbon capture, carbon utilization, hence the talk today. Dr. Angela Goodman is a research chemist at NETL Lab. She's developed quantitative statistical methods to provide policymakers with science-based assessments of large-scale carbon storage technologies and laboratory-based characterization tools to quantify the chemical reactivity of subsurface geologic formations. She holds a bachelor's in science degree and a PhD with a focus on physical chemistry and environmental science, and she's worked at the United States Department of Energy's NETL laboratory for almost 20 years. She's currently a technical lead for carbon storage for research on subsurface carbon storage technologies. And with that, I'll pass the baton over to Angela and thank her very much for her talk today. Angela, it's all yours.
All right, thank you, Alan. Thanks for that nice introduction. And thanks everyone for joining. This is a nice opportunity. It's an honor to present today. Okay, I'm gonna get started. Okay, so I'm with the NETL, and it's one of the 17 national labs. I'm actually at the Pittsburgh site here, and there's a site in West Virginia and also Oregon, and we have some small offices in Alaska and Texas. So I'm just gonna spend some time giving some background on NETL and why we're doing these measurements, and then I'll talk you through the statistical methods and tools, and then I'm gonna go through and do a live demo of the tool itself. Okay, so just a few background slides for NETL. I'm just kind of showing you what the workforce is, and we are the only government-owned, government-operated national lab of the 17 labs. And our mission is primarily to enhance the nation's energy foundation and protect the environment for future generations. And so our vision is to be the renowned fossil energy science and engineering resource to the world. Okay, so we do focus on fossil energy, and it's important because even now with renewables coming online and lots of advancements taking place, fossil energy still accounts for 80% of our energy for residential, commercial, industrial, transportation, and power. So it's really important that we use those fossil energy resources responsibly, environmentally friendly, because they are a big chunk of our energy portfolio. And it's likely to continue onwards to 2050. Right now, there's 6 priorities for fossil energy, as shown here. And I have highlighted in the middle is the priority that is a focus that I've been working on probably the last 20 years. It's just reducing the cost of carbon capture, utilization, and storage. So this talk will focus on CCUS. And this just shows a timeline of how carbon capture and carbon storage kind of go together. So there's a large group working on capture technology and storage technology. And then by 2025, these two will come together and we'll have an integrated CCUS project. And then by 2035, hopefully it will be available for commercial deployment. Let's see. So the main question is, how much CO2 can you store on the subsurface? So that's going to be the whole focus of this talk. And it's a resource assessment. So you trap the carbon dioxide, you transport it, and you inject it. Well, how much can you reasonably inject? So what we did is we looked at the United States as a whole and parts of Canada and just looked at it from a national scale. At a national scale, how much CO2 can you store? And so we worked with the regional carbon sequestration partnerships, which is, there's 7 of them across the US and parts of Canada. And the DOE and NETL put together a carbon storage atlas. There's 5 of them now. They come out every few years, where the partnerships assess CO2 sources and CO2 sinks, and they use the methods that I'm going to talk about today to estimate storage. So for oil and gas, coal, and sailing on the onshore, the low estimate is here and the high estimate is here in billion metric tons or gigatons. And so if you just look at the low estimate itself, that's about 400 years worth of storage. So there's a lot of storage available at this very high level. Okay, and this is just another glimpse of the 5 storage atlases that are a good reference, and then just visually showing how much storage is available in oil, unminable coal seams, and sailing formations. And then this is just a look at NETL's regional carbon sequestration partnerships. There's 7 of them in these different regions. And then there's a newer initiative called Carbon Safe, where there's 13 pre-feasibility projects and 6 feasibility projects. And so the partnerships injected about 1 million tons of CO2 in various formations, and Carbon Safe is working on injecting 50 million tons. So it's approaching the commercial scale of Carbon Safe. Okay, so this is just a snapshot of what we are looking at. So we're looking at the national scale, so the US and parts of Canada. And just to say that the methods and tools I'm talking about today are readily applicable to any parts of the world, and are actually lots of agencies around the world have used these tools, but I will focus on the US and Canada for most of the information today. We look at the prospective storage, so it's more like the exploration stage, so the very beginning of characterizing a potential region. We calculate mass resource estimates. So this is our mass resource estimate here. We look at it from a volumetric perspective. So we're looking at the total area, the gross thickness, the total porosity, and the density of the CO2. So that's how much pore space would be available. And then we have an efficiency term, this E-sailing, that kind of cuts down, well, what portion of that total porosity could you actually use to store carbon dioxide? We have a lot of statistics to back up our methods, and then we make everything available on our Energy Data Exchange, or EDX website. And also the information is available in these hard copy carbon storage atlases and also in the peer-reviewed journal. That's kind of a snapshot of what I'll be talking about today. Okay, so we've been working on this a while. Back in 2007 and 2008, these first two atlases came out. And this is an effort from all the regional partnerships working together with NETL to develop methods to estimate CO2 storage. So it's a huge collaborative effort at the beginning, and it still is. And by the time the third one rolled around, we took the original methods and estimates and we refined them, and we added better statistics and better data because there was hardly any information available during this time, but some more came available. So we updated and refined the statistics. Then we continued on, we developed methods for, originally with saline, coal, oil, and gas. Then we did it for shale, and we took another look at the saline by refining the saline method. We developed a screening tool called CO2 Screen. And then last we did residual oil zones, and now we're busy refining storage efficiencies again for the saline. So it's a evolving process, and it's been going on for some time, and it's a huge collaborative effort. I have some agencies here at the bottom. The USGS collaborated with this effort, the EERC in North Dakota, Illinois State Geologic Survey, Los Alamos, and I'm probably missing some, but it's a huge collaborative effort. Okay, so before I get started with the methods, we base everything on NETL's best practice manuals. So through those 7 regional carbon sequestration partnerships, all the lessons learned and the information that they derive from those projects are documented in best practice manuals. And the one I'm talking about is site screening, site selection, and site characterization. So in this manual, it kind of walks you through like, how would you do an assessment? So first you would identify a site or a basin and identify some potential subregions in that basin. And then the methods you would use to estimate CO2 storage, you would be at the prospective storage resource. So this on the right is the CO2 classification table. So on the left side is what the petroleum industry, the language they use, and this is what we're using for CO2 geologic storage. So at the top with your reserves, where you're producing oil, that would be reserves. When you're actively injecting in a commercial large-scale carbon storage project, you would be talking about storage capacity. So these are commercial, active injections. Then going down, you have contingent resources. So you're developing them. You also have contingent storage resources. So you know a lot, but you're still developing them. Now the prospective storage resource, which I'm talking about today, is very exploratory and at the initial phase. So you're identifying these potential subregions, and you're shown here, and eventually you could get to the selected areas and potential sites and qualified sites. So the methods I'll tell you about today can work for these first 2 regions, but as you get to sites and qualified sites, you're going to need better models. Commercial simulators can include a lot more information. So what I'm telling you today can only be used at the early phase. Okay, so in these best practice manuals, this is a flow chart I grabbed for site screening. So for example, you identified your potential subregion here. And so you kind of have to walk through, well, what's your regional geologic data? So you have to identify, well, what storage formation are you looking at? Is it at the right depth? So when you inject CO2, you want it to be in a very dense state, which could be liquid or supercritical. And then you have to have a seal. It has to be contained laterally and vertically. And then it also needs to be able to accept that volume of fluid that you're injecting. So if you go through all those, then you can start looking at the regional site data. So if you select a subregion, you could say, well, are there any protected or sensitive areas? What about population centers? Is it a large city there, or are there no cities, small cities? And then there's existing resource development. Are there resources you can already use? And then you might use a pipeline, but do you have the right of way for that? And then you can move on to the social data. So what are the demographic trends for that area, and what are the the traditional land use for that particular area. So once you get through all this of identifying your potential subregions, then you can move on to your selected areas. Okay, so I'm going to start talking about the saline method first. So this is our methodology for saline formations. So this is that subsurface data analysis that I just showed you on the prior page. So we're targeting saline formations, and it has to have a total dissolved solids, or TDS, above 10,000 parts per million to be considered. You have to have it at the right depth, and usually 800 meters is, you know, a cutoff that people recommend, but you know that can be flexible. You need a seal, confining zone, and you have to be able, the formation has to be able to accept that change in pressure to accommodate the planned injection volumes. So this is the equation I went over earlier. So you have your area, thickness, porosity, density, and then this is your efficiency factor. So essentially you can use, if you don't know much about your system, you can just use an average value for area, thickness, porosity, and density. If you know a lot more about your system, you can use a mean and a standard deviation, or you can grid your formation into several grids and have a different area, thickness, porosity for each one of those grids. So the tool I'm going to talk about later will show you how you can accommodate how much information you have about that system. Now the efficiency term here is going to reduce the pore space into the amount that could be possibly stored. And this efficiency term is broken up into 5 terms, and we treat this efficiency using a log odd stochastic approach. And the equation is written here. Essentially, you have your net to total area, net to gross thickness, effective to total porosity, volumetric displacement, and microscopic displacement. And so when you go through all the calculations, what you end up is a low and a high value. So you have your P10 and your P90 value for storage assessment. So when you look at this table here on the right, these are the low and the high for 3 different lithologies for saline. And then that translates to what I just showed you earlier in the carbon storage atlas. So all 7 partnerships reporting for saline onshore, and here's a low and a high value. So, okay, so that's how you calculate storage efficiency. So the input values that go in the storage efficiency come from this table on the left. So this is a table of values that were put together by the Energy and Environmental Research Center, the EERC, and in collaboration with the IEA's greenhouse gas program. So for example, your net to total area, let's say you're considering maybe 20 to 80% of your formation is going to be available. Or if you look at your effective to total porosity, maybe for the limestone, 60 to 70% is going to be effectively connected. So these are the input values that go into these storage efficiencies to come up with these overall efficiencies. So essentially between 0.4 and 5.5% of the formation is going to be available for CO2 storage. Okay, so right now we are working on updating those or refining those storage efficiencies. So the prior data I showed on the left was based on a handful of experimental results on relative permeability and residual saturation. And we are now collecting, or we have collected data on residual saturation and relative permeability for, on the graph on the right shows 12 to 13 different depositional environments. So we have an updated data set, and we are working to plug those in and update the storage efficiency factors. And this database is available online through EDX if you're interested to look at it as well. Then this table just kind of shows the different lithologies and depositional environments shown by the graphic behind it. Okay, so I'm going to move on to the shale methodology equation. So just first off, it looks a lot more complex than what I showed you for the saline, and that's essentially because you have storage as a free gas, and like the fractures, natural fractures, hydraulic fractures, and pore space. And then you also have sorption, so CO2 can sorb on the clay and the kerogen components. So before I go over the equation, if you look at the subsurface data analysis, so we only consider shales where hydrocarbons have already been commercially produced or expect to be commercially produced, and they have to be stimulated through hydraulic fracturing. If the shale isn't stimulated by hydraulic fracturing, there's no space in the formation to inject the CO2. Again, even with the shale, you have to have it at a sufficient depth to make sure it's in that supercritical or liquid state. And you do need a seal. You might even need a secondary seal. That's another shale in addition to the shale that you're storing in. Okay, so moving on to the equation. So you have your net effective volume out front, and then you have your free phase in this term and your sorb phase on the second term. Again, we use a log odds stochastic approach to estimate the storage efficiencies. And so I will walk you through that. So what we did is we used a model NFlow and FracGen to generate storage efficiency factors for free phase and sorb phase CO2 in shale systems. So we did a lot of different scenarios. We looked at the little greens are the matrix fractures, and then the I guess the red or magenta is the hydraulic stimulated fracture. So we did a lot of different injection scenarios, a lot of different fracture patterns. We probably did maybe 25 to 30 different injection scenarios to come up with these efficiency factors here shown on the right. So we have the free phase and we have the sorb phase. And this time they are categorized by time. So these are time dependent. So in 10 years or 20 years or all the way to 60 years, you can see how the storage efficiency changes. So essentially the free phase is about between 0.15 and 3.36%, and the sorb is between 0.1 and 0.2%. So much smaller than what you get for the failing formations. Okay, and we also continue to do some refinement of these shale storage efficiencies. On the left, we looked at different flow regimes that you might find in a shale regime or shale formation. So you have regime 1, and this looks at linear flow inside the stimulated reservoir. Regime 2 looks at it flow towards the stimulated reservoir. And then this last one is a pseudo-steady radial flow. And we did this to look at, well, how does the pressure distribution change in these formations? So regime 1, here's a snapshot at 10 years. Regime 2, a snapshot at 60 years. And regime 3, a snapshot at 60 years. So this just gives you an idea of what that pressure front's going to look like in the shale formation. Now, the work on the right was primarily performed by the EERC. They did some really nice work with scanning electron microscopy, where they did some high resolution imaging, and they were able to take the shale equation and take that sorb term and parse it out into sorption onto clay material and sorption onto organic matter, which is OM here. So they did some high resolution imaging, and they looked at these shared borders of, say, an organic and a clay, and they were able to distinguish, well, there's going to be this much space available for sorption on organic matter versus absorption on clay material. And so they had added some equations to the existing equation for shale that I showed you in the prior slide, and they were able to come up with an expanded method that accounts for the sorption term better. Okay, so I'm going to move on to the residual oil zone method next. Okay, so essentially residual oil zones and saline formations are very similar, except that residual oil zones have some oil in them. So essentially with our subsurface data analysis, we looked at ROZs, residual oil zones, that were not produced prior or during CO2 storage. But if you have a residual oil zone that uses CO2 for enhanced oil recovery, then you need to have a different method to account for CO2 storage. So you can use this method before production or after production. And again, you have to have that sufficient depth, and has to have a seal, and has to be able to accept the injected volume. So this equation looks complex, but it's actually the saline equation that I showed you earlier, plus one term added for CO2 dissolution in the oil. So essentially we do our log odds stochastic approach with the efficiencies. We report the P10 and P90, low and high. Okay, so this is some of the terms expanded. The only new terms in this equation is we had to add the residual oil saturation, and then the amount of CO2 that could be dissolved into the oil, and this last term, EDS, which is the fraction of CO2 dissolved in the oil phase. So there's only 3 new terms in this equation. Okay, so I'm just going to show you an example where we applied this ROZ methodology. So I told you we only introduced 3 new terms, so we knew all the other ones except those 3. So this table will show you we knew the area term, and we got all those values from the literature, the thickness, the porosity, the pressure and temperature. Now the dissolution of CO2 in the oil, we had to simulate that. And for this particular project, we used MRST, but any simulation tool could work. And the efficiency parameters, we also knew those from the literature, primarily from the EERC's database. And then we simulated this last term, the efficiency of CO2 dissolution into the oil. And so what we did is we had a high scenario and a low scenario. And the high scenarios where we assumed there was 38% residual oil saturation, and the low is we assumed there'd be 20% residual oil saturation. And so the whole point is that even for the high scenario, about 90% of the CO2 is stored in the free phase and only 10% dissolved in the oil. The low scenario is even more CO2 in the free phase, 97% versus 3% in the oil phase. So if you didn't know a lot about your residual oil zone that you're assessing, you could substitute the saline equation for it and get an approximate answer. Okay, so next I'm going to go on and talk about the tool itself. So all those equations and methods I just talked about, we have them online in a screening tool that's available to the public and free. And so we called it CO2 Screen, Storage Prospective Resource Estimation Excel Analysis Tool. There's 4 versions. We started with saline, then we added shale, we added residual oil zones, and then we converted everything to Python. So the first 3 we're done with GoldSim and Excel, and the last one is done with Python. And it's been downloaded a lot, over 600 times since 2017. So there's a lot of activity with this tool. Okay, so if you go to this website, NETL's website for EVX, and you type in CO2 screen or any of these keywords here at the bottom, you will come to this screen. So you have an option to download the Python or the GoldSim. You just download it. There's going to be a window that pops up where you can put your information in and identify who you are, or you don't have to. It's entirely up to you. You can download them from this website. And so when you download it, I'm going to go over some screenshots here, and then I'll go into the live tool. So this is the GoldSim Excel version. So essentially there's a Excel sheet that you put all your information in, and then you run the stochastic modeling with the GoldSim player, and then your output is in the Excel worksheet. Okay, and then this is an example. So when you go into the program for the Excel sheet, you go type step 1, you can put your name and information in. Step 2 is identifying your storage efficiency factors. So there's a pull down menu here, and there's 13 different choices that auto-populate for efficiency. Or you can put your own values in the green. And this is just the program calculating the log odds statistics here. And then step 3, you go to the physical parameters. So you'll put in your area, thickness, porosity, pressure, temperature. And then if you wanted to do step 4, which is a grid specific, so say you had different values for each one of your grids, you would just enter them there in the user specified. Okay, and then you can see at the tabs here at the bottom, there's the saline, there's shale from the EERC, and there's residual oil zone. So all of the methods and tools are in this one sheet. Okay, so then this is a close-up, for example, for the saline formation, entering your efficiency factors. So this example shows that you chose delta for your lithology, depositional environment. but you could enter your own values here. And then this is an example for the shale. Remember I told you that it was time dependent, so you could pick 5 years, 10 years, 20 years, whatever you wanted to pick there. Okay, so this is the physical parameters. This is just an example. So you have your area, your thickness, porosity, pressure, and temperature. And a lot of these values are the same, but you can have different values for each one of these grids. And you can have up to 300 grids in this GoldSim version. Okay, and this is what the GoldSim player looks like. Essentially, you select, are you doing shale, saline, residual oil zones, or shale with the AARC. Select which one you're working on and then click play. It takes just over a minute to run. And then this is what your output looks like. So you can have, for each of your grids, your P10, 50, and 90 storage resource, what your environment was, and then what the individual saline storage efficiency was. Okay, moving on to Python. So when you open up your Python, this is what it looks like. Then you kind of just follow these tabs here at the top. So first step, pick your formation type, saline, shale, residual oil zones. And this is a lot less visual than what I just showed you, so you can refer to the peer-reviewed articles to understand what it is you're choosing with the equations. Physical parameters, so you enter your area, thickness, porosity, pressure here. And this is for residual oil zones, for example, irreducible water saturation, residual oil. And you can enter a standard deviation, or you can just keep it at the average value, your choice. And this is an example where you're on the next tab for efficiency factors. So you can have that pull down menu and you can select which one that you want. And this is, or you can just say unspecified, or you can add your own information. So however suits, whatever suits your analysis. And then we'll move to the last tab, the outputs. So this is what your output looks like after it's run. And I think you have to click run in this tab. And then if you click on the outputs tab, it will take you to the Excel file. So everything dumps into an Excel spreadsheet again. Okay. So this, what I showed you is just for a single grid with Python. If you wanted to do multiple grids, and you can do unlimited grids here in Python. What you do is you prepare your own Excel file for your physical parameters, and you prepare your own Excel file for efficiency factors, and then you'll have an output file with everything for each of the grids that you provided data for. Okay. Couple more things. We do have an article where we applied the tool to the Oriskany formation just to kind of walk through as an example. And this is one of the regional carbon sequestration partnerships, the Midwest Regional Carbon Sequestration Partnership. So they identified the Oriskany formation as a potential storage reservoir for CO2. It does have abundant pore space, it's at the right depth, and it has a good seal system above it. So we looked at some well logs. There were 5,700 well logs. We only looked at it in the state of Pennsylvania, and we looked at depth, thickness, porosity, temperature, and pressure. And we plugged everything into the screen tool. We did the calculation, and then we used ArcGIS to map it so it's more visual. So this is just an example of what the storage resource might look like for the Oriskany formation in Pennsylvania. And then there was an external application of the screen. This again is the Midwest Regional Partnership, where they assess the Northern Michigan Basin, and they use the screen tool, and this is what their results look like when they mapped it using ArcGIS. Okay. So just to kind of go over this, so we have statistical methods, and we know even with the low estimate that we have about 400 years of storage space available. These tools and methods help with deciding for energy policy for CCUS. Like I said, other nations worldwide are using this tool. It is very available. You can see it in the peer-reviewed journals, it's in the carbon storage atlases. It's online through EDX and also at the GoldSim website. And it's a huge, highly collaborative effort. The partnerships are involved: Carbon Safe, USGS, EERC, Illinois State Geologic Survey, CMU, NIST, Los Alamos. it's just a huge effort. And it's really helpful for making those business decisions and investment decisions. And so these estimates at this high level are important because if you're planning drilling patterns or monitoring activities or pipelines, you want to make sure that you get this right, because you don't want to build a pipeline and have it be in the wrong spot or have it not be useful. So you don't want to waste resources. Okay. And then just for future work, we do have the Python. We're working on putting a graphical, a ArcGIS capability so that we can make the graphs of the results a little more available. This is just a list of the groups that did register when they went on the EDX website and downloaded the tool. Like I said, it's not required to register. And then we are updating those storage efficiencies based on experimental data. So these are just the references if you want to read the peer-reviewed literature. And then that's all I have for the PowerPoint, but I'm going to walk you through some of the tools themselves online. But before I do that, I really want to give thanks to my team, the partnerships and Carbon Safe. Sean Sanguinito, he did the majority of the work for the screen tool. He did a very nice job with that. Fuad Harry really worked hard to set up the Python. Eugene Mishaken worked hard for the modeling with NFlow and FratGen and MRST, and just all my colleagues here at NETL. And I just want to thank Scott Fraley, Charlie Barecki, Wes Peck, Peter Warwick and his team just for their technical advice and contributions, and making sure that these methods are based on, science and the correct statistics. So I just want to thank everybody. Okay, so I'm going to move over to the live demo here. Okay, so I'm curious, can you see my screen or just the PowerPoint at this point? Do I need to share something else?
We still see the presentation, Angela.
I have to share, let's see. Okay, so I'm going to share a few apps I can, get this done. Okay, so you can see maybe this Windows Explorer right now.
Yes, we do.
Okay, so when you go to the website, you're going to download, you'll see CO2 screen version 3, GoldSim, or version 4 Python. This is kind of what you'll get. So you'll get a user's manual. This is the GoldSim player, and then this is the Excel sheet. So I'm probably going to have to share each of these as I open them. So what you want to do is open up the Excel sheet, and I'm going to share that as well. Okay, so now you can see the Excel sheet, I hope. Okay, I'm going to assume that you can. So this is the what you would get if you were working in the GoldSim. So there's the saline inputs, saline outputs, shale input, output, the EERC, shale, and the EERC output, and the residual oil zones. I'm just going to stick with saline for the time being and just kind of walk you through this. So here's your information. You can go here and do the storage efficiency. So there's this drop-down menu. You can just select whatever lithology you would like. You can also enter data in here directly. You just have to make sure they're between 0 and 1 because it's a fraction. You can't go over 1. So you could enter information there. And if you're not using something, just put 0 and it won't be read. And then there's the physical parameters. So this is your area, thickness, porosity, pressure, you just enter whatever you want, or you can cut and paste from another spreadsheet. So then you save that file and you have to close it. And then you go back here and open up, whoops. Okay. Oh boy. Okay, I'm going back to this screen and now I'm going to open up the GoldSim player. Okay, so this is what the GoldSim player version looks like. So you can see these are for the saline, the shale, the residual oil zones, and the shale with the EERC. So you can kind of look around in these boxes, and this is
Yeah, it hasn't showed up, Angela. We're
it
still
didn't
looking.
show up. Okay, let me share again here. You share. Okay, how about now?
Yeah, I see 4 boxes.
Okay, thank you. Okay, so this is what it would look like in the player. So let's just take a look at the saline one. You can kind of look around, and these are all the equations. So this is the log odds equation that's already been incorporated into the tool, and the porosity and its distribution and things like that. This is actually the lookup table for calculating density. So you have your pressure and your temperature here, and the values that go into calculating density. So you don't have to do anything to this. You actually can't edit it at all. But if you want something to be changed, just contact us and we will be happy to do that. So you just hit play and, well, I guess I need to select. Okay, I did select saline, but you hit play and it runs, and like I said, it takes about a minute to complete. So while that's running, you can go, we're going to look at the Python version. So I'm going to go over here and open up the Python. So I'm assuming you can still see this kind of Windows Explorer screen. So the Python is this .jar application. So you can open this up. And I will share that as well.
We're still looking at GoldSim, Angela.
Still looking at GoldSim. Okay.
Oh, it switched.
Did it switch to Python now? Okay. All right, GoldSim is still running, so we're going to let that run. So Python, this is what your screen looks like, and you just hit OK. And this is sort of the, I don't know, screen that it takes you to first. So what you want to do is go over here and select saline, shale, or residual oil zones. We'll just do saline for consistency. You go to this next parameter and you can start entering any value that you'd like. All boxes have to have information in it. So I don't know, you'll probably have better data if you're doing this on your own. But so you just enter information there. Then you go to the next tab for the efficiency factors. You can select from these 13 different choices what kind of lithology and depositional environment you would like, or you can just enter your own. But again, they have to be between 0 and 1 in order to work. And then you would click run on that one, and that one takes, I don't know, probably a minute. But I'm operating on a small laptop, so if you had a decent computer, it would go faster. Okay. This one seems to be stuck. Okay, there it is, simulation complete, and everyone can see that. So you just hit OK, and then you go back over to your Explorer app, and you'll see that your Excel spreadsheet has been just updated. So you open that up again. I probably need to share that.
Yeah, we are not seeing that page.
Okay, so I'm sharing the Excel spreadsheet now. You head over to the saline outputs tab, and these are the new values that, that the tool calculated for you. So you have the low, mid, and high for each of the grids. You have your depositional environment, and then you have your storage efficiency for each one of those grids. And then you kind of have your storage statistics summary here. So it's pretty simple to run. I'll move over here. So the Python screen is now done. So I'm going to go back over here to Windows Explorer into Python in the formation apps. Okay, wait, I don't really need to do that. So I go to the Outputs tab, and here's the outputs. For the,
You got to share it with us, Angela.
okay, I didn't share that. It seems like it's unsharing itself. Thank you, Sean. That's Sean Sanguinito. He did a lot of work putting this together. Okay, so after the Python tool is developed, or as it's run, you go to the outputs, and this is your result. And you can click on this outputs tab here, and it puts it into an Excel sheet. So can you see that Excel sheet?
Not yet.
Probably need to share it again. Okay. So that's what this looks like. Okay, I just want to tell you about one more feature, and then we can open up for questions. So I'm going back to the Python tool itself, so hopefully you can see that. So everything I showed you so far was for one grid. You can also use something called multiple grids. So
We're still in the Excel. Sorry.
Oh, okay. Great. Back to Python.
There we go.
Okay, so back to Python. So everything I showed you before was one grid. So if you want to do multiple grids, say you have 1,000 grids in your spreadsheet, and you want to load it into this tool, that's no problem. So all these boxes you cannot fill out anymore. You have to go to the inputs for Python. Can you see Windows Explorer?
Not yet.
Okay.
Now I can.
All right, thank you. Okay, so you go back to here, and there's formation inputs. And so I'm just gonna start with the saline. So open this up. So what you can do is populate. I probably need to share that again. Okay, so I think you should be seeing the Excel sheet. So this is the sheet, and you would just populate this sheet with whatever grids that you want. And I think it's unlimited for Python with all the information that you need to put in for the program. And then you would save it and close it. And you would go back to your Python, and then you would click run, and it would take all the information from the Excel sheets. And I'm not going to show that output because I had to share like 5 more things to make that work. But I'm happy to answer any questions if anybody wanted to ask questions now.
Alan, are you there?
Yes, yes, I had a slow mouse, I'm sorry. What's interesting is that people will ask a question and then somebody will come in and kind of build on it. So let me start with one that I asked that I will share with everybody, and then Sean kind of came in. You know, we know in the oil industry that when we use a broad classification like delta or turbidite or something like that, that distinguishes shallow water from deep water deposition, but those models have a lot of variation in rock properties and so on. In a deltaic model, there are channels, there are distal facies, there are inner and outer fringe, there's prodeltaic. You go from proximal to distal. Same thing in the turbidites. So I was wondering if we're using a very broad classification here, and if we're going to subclassify it, and Sean said the delta values and all the depositional environment values were taken from a 2009 report by EERC, and we're currently working on this to get new and updated simulations to get improved values for each depositional environment, and then each subunit, I would say, in each of the depositional environments. So I just wanted to share that one. And then there was something from Richard Schultz that looked like Richard Esposito might have answered. So Richard Schultz says current CCUS in the United States focuses on EOR. Not looking at Richard's response, we'll just read this and ask this to you, Angela. How do
Okay.
you see actual carbon CO2 storage being implemented given our distributed sources and related jurisdictional complexities?
Okay. So how do I see storage being implemented with this different sources, and just maybe say that one more time.
Yes. So in the US, we're focusing on EOR. That's the CCUS ties to EOR. How do you see actual CO2 storage being implemented given our distributed sources and related jurisdictional complexities?
Okay. So when I talked about in the PowerPoint, which there's regional partnerships
Yeah.
and carbon safe, right? So they are working on, going through permitting and working with the public and attempting to, inject those commercial scale volumes. And then all that information is compiled in the NETL best practice manual. So there's a lot that goes into it, and there's a lot of complexity, permitting, getting, the right pipelines and the costs and all that. So I wouldn't say that's all ironed out, but there's, they've been working on this since probably 2001. And so all that information is concentrated in the best practice manuals, and there's at a smaller scale, but at this 50 million tons commercial scale, there's going to be a lot more new lessons learned and new information available. And NETL does have a cost analysis team where they look at different scenarios about how to do pipelines. Like, should you have a dedicated pipeline? Should it be a truncated pipeline? Where should the pipelines go? So people are thinking about that. I don't think that the final answer is out there.
So thank you for that. Now, Richard, who can speak for himself, but apparently I'm reading all these questions here, says regional storage hubs may be used, sort of as an answer to this question. Regional storage hubs may be used, but in many parts of the country, some emitting facilities will have good source sink matching with saline reservoirs, both onshore and offshore. New sitting for fossil facilities will likely include a component of geology as related to potential storage options.
Yep.
Okay, I think there are so Jeremy Boak had a question. You used the term grid. By grid, do you mean grid cell?
I do mean grid cell, yeah. You can make them whatever size that you want.
Here's a good one from Mahdi Haddad. So I'm assuming to get started, I'm building up on his question. I guess you get an EDX account first and then you get to the software. Is that how that works?
I don't know if you need an EDX account. This is on the public side of EDX.
Okay.
You should just be able to download it. There's some kind of information window that pops up, but I don't think you are required to fill out the information.
Okay, so now Mahdi's question, which is really good. Thank you for this great talk. Are there instructive and publicly available manuals for these software packages?
Absolutely. I forgot to mention that, but under, and I don't know if you can see the screen. I will just share one more time. There's always a user manual that comes with it. So here's a user manual for the Goldson version, and there's a user manual for the Python. So they walk you through how to run everything. Do not know how to share that one, but there we go.
Yeah, that's great.
Yeah, so here's a user manual that walks you through how to use it all.
Perfect.
Okay.
Perfect. So I noticed that there are a number of companies and facilities that are using this software. I only remembered quickly scanning the list. I saw ExxonMobil and I saw BP. Are there other oil companies that are using this yet?
Unfortunately, we don't know specifically who uses them unless they share their name and information when they download. So
Okay.
only if they decide to tell us, that's how we know. Or if they cite us in the peer-reviewed literature, which there's a time gap between maybe like when someone uses it and publishes the results.
Okay. Are there any other questions or comments that the audience has? Before I forget, I want to thank Angela for a fabulous talk, a very nice piece of software. This is being recorded, and we'll try to publicize this and let you know how we're doing that, but we'll try to draw attention to the fact that this seminar has been recorded and the software is available and there are user manuals. Does anyone from the audience have any follow-up questions or comments?
I had a quick question, if I'm unmuted yet.
I can hear you. Yep.
Okay. The presentation, some of the slides are quite useful to refer back to. Will that also be available to us?
Yes.
Great.
Oh, well, you'll be able to see an image of the slide. What you're asking is, will there be a PDF available? Is that possible, Angela?
Yeah, I sent one this morning to you guys.
Okay, good.
Yep.
We'll make that available then.
Mm-hmm. That sounds good.
Well, thank you very much. An
Okay.
excellent talk, good exchange of information, and thank you again for doing this.
All right. Thank you so much for the invitation, and thanks everyone on the line for all your questions and your attention. Have a great day. Thank you.
Thank you. Thank you.